research in energy and vehicles titled Empower Public Transportation with Dynamic Incentivization Services by Dr. Tang, who is currently an assistant professor in the University of Regina, Canada. Her research interests include urban mobility, transport economics, and system optimization. Dr. Tang has 10 years of integrated experience in both industry and academia in Canada, United States, China, Hong Kong, Denmark, and Japan. She won over 6 awards in research and entrepreneurship in the past 5 years. Dr. Tang has contributed and collaborated in a variety of research projects with University of California, Berkeley, Technical University of Denmark, Research Grants Council of Hong Kong, and Alibaba Group. She has published in top-tier journals and given a number of invited presentations in prestigious international and local conferences, workshops, and seminars. She proposed a Nobel Fair Reward scheme in 2015, and the fundamental paper was one of the most cited articles published since 2018 in the top-tier journal Transportation Research, Part B. Thank you very much. We appreciate your participation, Dr. Tang. On the other hand, to all the assistants, please, if you have any questions, you can send it via chat and we will address it at the end of the seminar. Without further ado, I give the space to Dr. Tang so you can begin with your presentation.
Thanks, Adrian, for introducing and the invitation. Hello, everyone. So it's nice to meet you virtually in the seminar. And let me share my presentation today. So today I'm glad to share all of you about our recent progress that's for the dynamic incentivizations in public transportation. And we find some interesting results about that with appropriate and scientific design of the incentivizations, it can reduce the congestion as well as maintaining the providers, operators' revenue, which is one of the key progress that in the pricing and incentivization areas. So particularly today's seminar I'd like to share is about one of our research with the Technical University of Denmark and the Hong Kong University of Science and Technology, and which was published in the Transportation Part B. And this research was talking about the fare incentives that's such like a surcharge and reward scheme that to help people to relieve the peak hour congestion, smooth out the traffic flows that in the public transportation systems. The ideas are driven from the peak hour commuting problems in many metropolitan areas, like in Tokyo, Hong Kong, Beijing, Copenhagen, that the long-term queuing and crowding that have decreases the passengers' satisfaction, and also that the peak hour commuting also have induced the overcrowding passenger flow that increase the safety and security risks for the transportation system resilience, as well as the overall operations. However, that to improve the transit service is expensive and also time consuming if it involves constructions and all the reversions for it. So these two graphs are showing the peak hour flows in one of the Beijing stations, where morning peak consists of almost 62% of the overall daily flow. So such like peak and valleys that during the day in many of the public transportations have caused a lot of inconvenience, also insufficient capacity utilizations. And there are a variety of the demand management strategies implemented or researched over the world in different countries and regions. Like in Hong Kong, that there is 25 off-peak discount. In Copenhagen, that there is an off-peak discount in the midday. And Singapore has free peak travels, while Melbourne, Netherlands has some early bird programs. But the existing demand management strategies are either the pure surcharges, which It's more like act as a penalty and decreases public acceptability. While for the pure off-peak discount or fare-free strategies, that it causes transit operator revenue loss, which is not financially sustainable and cannot last for long because of the requirement of a vast amount of the subsidies. And also for pure off discount and free fare strategies, it attracts untargeted passengers who would otherwise traveling by walking or by bikes, which also attract this unnecessary demand to the public transportation and further worsen the above situations. So the idea that we have is proposing a surcharge reward scheme. It is in the sense that commuters will incur the surcharge for trips during the predetermined central period, while all the surcharge will be refunded and accumulated in commuters' personal accounts, then can be used during the shoulder periods. So commuters will be able to use these rewards for each trip from the account balance accumulated by the previous surcharges, but they're not to use this reward if the account balance is less than the value of the reward. So this coherent design criteria has first ensured that for commuters that they both have they're incentivized to use their account balance during the off-peak hours, which can modify their behaviors and encourage some of the passengers to shift from peak hour to off-peak hours. And it also keeps the balance of the operator's revenue in the sense that the operator in the overall system that didn't lose their benefit because to provide the subsidy, and also they're not gaining the revenue for no reason because of the surcharge, because all the surcharge refunded to commuters' personal account. So this means that, like this three picture shows here, that generally in many metropolitan transit systems, that they have original fare from one origin to another destination. And then with this surcharge reward scheme, a commuter for one day while traveling in the peak hours with surcharges, however, he may become a commuter with rewards in the other day if he traveled in the shoulder periods. So this actually also introduces the dynamics in the transit system that are worth to modeling and to evaluate what is the effects of this surcharge reward scheme. Now, how it changes the travel behaviors as well as reduce the congestion and crowding in the transit system. So there is an example here that may help you better understand how this idea works and how this scheme works. So let's say that there is initial fare that is like P0, and the peak period is from 7 to 9 a.m. in the public transportation system. And then with this SRS, that we define that from 7:45 to 8:45, this is a central period. And if commuters travel within this period, they get a surcharge data S. However, on the other day, if they travel, I'm sorry, because someone entering the waiting room, so I need to admit this. So so then from 7:45 to 8:45, then it's central period. And then if commuters is traveling this period, they get the surcharge data S. Let's say 5 krona. So krona is a money unit in Denmark. We use the Denmark case studies in this research. So let's say they have 5 krona during the peak, and then on the other day they may use this 5 krona during the off peak if they travel between 7 to 7:45 or 8:45 to 9. Then Under this kind of scheme, then a proportion of commuters will be induced to shift their departure times, and therefore the passenger flow congestion will be smoothed out over time. So this is kind of individual-based and also incentive-compatible strategies that's different from the current anonymous strategies, which didn't count for the individual preferences and their heterogeneous departure times. And to evaluate the effect of these strategies and also to model passengers' behaviors in a peak period, that we further develop the models. The first model that we developed is for the traffic assignment model, that to figure out what is the ridership for the buses during the day, for the time of day. So this behavior model is based on the passenger's generalized cost, where we consider that passenger incur a queuing cost, schedule delay cost, crowding cost, and freight cost when they're taking the public transportation. And when so in the public transportation, that all the buses or either subways are running in the discrete schedules, such as departure at T1 to 2 TM. So the x-axis for here means the discrete departures, while the y-axis, it means the number of stations. So when for passengers that taking the service round M, which let's say depart at TM, and then he will incur all these costs that depending on the departure time of this service round. And the schedule delay cost is a cost that to quantify passengers' costs when they arrive early or late to their working time or to their preferred time. So let's say that a passenger need to work at 8 a.m. So if he arrives at 8:30, then he incurs a scheduled delay late cost. If he arrives at 7:30, then he incurs a scheduled delay early cost by 30 minutes. So this cost is widely used in the transport economics to quantify the passenger's trip cost. And then it's modeled as a linear function related to the departure time, as also at the value of time, which is beta and gamma here. And another very important cost that need to be considered in transit is a crowding cost. A crowding cost reflects the user satisfaction that is related to the number of passengers in the vehicle. So it is monotonically increasing with the number of passengers, NM, in a particular vehicle, and is a continuous function. It is also related to the D here, which is the time of which is in vehicle time. So it is a time that passengers stayed in the vehicle. So this crowding cost is related to the number of passengers and also the time that they traveled in the transit vehicles. So with this generalized trip cost function, that we can derive a user equilibrium condition. A user equilibrium condition is that no passenger can reduce his trip cost or her trip cost by unitarily changing departure times or use of service rounds. So this user equilibrium cost is a common is a typical concept in the traffic assignment modeling that to help us understand what will be the stable conditions for the transit systems. And then there is another condition which that queuing time is 0 if the service run is unsaturated, and it's no less than 0 if the service run is saturated. So if the service run is already saturated, this means that passenger need to wait for another buses, for another vehicle. So this is a bypass. There is a bypass queuing time that for them to wait for additional service round to get board, to get on the board. And therefore that with this equilibrium conditions and also this realistic conditions, we modeled the user equilibrium of departure time distributions. So in here, that the objective for us is follow so these mathematical models is follow the models of the Bateman function, which the objective, there is no economic interpretation of the objective. But however, to solve the optimization models, we take the first derivative of the variables, and then we will get a variety of the Lagrange functions, which reflect these two equilibrium conditions here. So this part of the models that shows what will be the distribution of the ridership in each service rounds. So let me show you a simulation that we're going to talk more later. So with this function, with these models, what we will get a distribution, which is the of ridership for each service round. And we will also get what will be the rounding service periods. So for this case, that with this model, what we simulate is that we find out from 6:30 that there's passengers start to board on the transit. And then the passenger boarding ending at 7:45 for the peak period. But of course, that in those off-peak periods, there's still some passengers. But while we are focusing on the peak period, those numbers are ignored. So, and then passengers boarding are increasing when it's close to the central peak period. So the x-axis represent the departure times of the buses, of the vehicle, or the subways. The y-axis represent the number of passengers in these service rounds. So then based on this model, which gives us the distribution of ridership before the surcharge reward scheme, and then we also need to compare what will be the ridership after surcharge reward scheme. And we want to optimize the performance of the surcharge reward scheme to maximizing the reduction of the congestion in the system. The next step is that we need to focus on the design for the surcharge reward scheme. What will be the appropriate design, and what will be the better design that to operate the system? As there are a variety or ultimate designs for such surcharge reward scheme, a bad design that will induce even more congested and crowded transit system. So there is one design criteria that this scheme is designed such that the trip cost that in the shoulder period are no greater than the central period. This means that if passengers have taken the trips in the shoulder period with rewards, then they will have less trip costs, or at least equal trip costs than those that are taking for the central period. So this causes an incentive constraint that will encourage passengers to shift their departure time to the shoulder periods because they have the reduced trip cost. And then mathematically that we have this formulation that represent this design criteria. And in this formulation that we have reward ratio, which means what is the number of trips with rewards to the total number of trips during the whole intervals. So this reward ratio also controls the value of the surcharge and the reward. It connected the value of the surcharge reward. So for example, that if we have a reward ratio which is 0.5, it means that when passenger take one trip in the central period, then he can get with $5. Then when he take, then he can get a reward equal to $5 in the shoulder period. So that is how it connects to the value of the reward, the surcharge and the rewards. And then our objective to minimize the total system cost. So the total system cost is a cost that we defined in here for the passenger generalized cost. So the sum of all the passengers generalized cost, that will become the total system cost. And then one will need to determine the decision variables to optimize the performance. First, it includes the central period duration. How long this central period should be? Should it be 30 minutes? Should it be 1 hour? Or should it be 40 minutes? And what is a central period location? It means when this central period should start. So let's say it should start at 7, or it should start at 8, or should start at 8:30. And then the value of the surcharge, and also the value of the rewards. Like whether, let's say, if the surcharge is $5 and the reward can be $1 or $2 or $5 equally. So all these three are the decision variables that will simultaneously affect the performance. So then this generates mixed integer nonlinear optimization problems, while the upper level is to optimize to determine these decision variables, which will affect the user equilibrium and commuters' generalized trip cost. And the lower level model is an equilibrium model, like I mentioned before, that to derive the distribution of the ridership in the transportation system that with different service rounds. So for this equilibrium, when we solve this kind of models, that we also derived a set of the interesting properties. So first is that we define that the efficient reward ratio, that all the service rounds shouldn't be empty within the central period. So for example, that with some designs that we may get a kind of distribution like this graph, where some service rounds are empty in the middle. So this is a waste of the capacity, and it also turns as not efficient design. The better thing that we shouldn't keep any empty service rounds at any intervals. And by this, and we can achieve this by adjusting this reward ratio here. And then there is an optimal central period location, which indicate that there is an interrelationship between the first service round and the last service round in the central period. So let's say if passengers have a preferred departure time, which at this black line shows, that if we put the central period all away before this preferred arrival time, which will induce more congestion. The best way is to put it similar to symmetric way, so that passengers can either depart. Some passengers will depart early than their preferred arrival time. Some passengers will depart late than their preferred arrival time. But they're kind of balanced, so the overall system costs are reduced. And there is some interesting findings of the theorems is that there is a lower bound of this surcharge, which means that the system performance will increase with the value of the surcharge and reward. And then after it reaches to a bound, to a certain value, then the system performance will keep constant. So that is what we call the lower bound of the surcharge. And also that to successfully implement these strategies, that there is also boundary of the crowding cost, which this indicates that the crowding cost should be strong or effective enough that to incentivize commuters to shift. So in some transportation systems or in some regions that people don't care too much about their crowding costs. So in this sense that this surcharge reward scheme may not that effective because people are not incentivized to shift. While in some regions, people do care about their crowding costs and the congestions. So they're willing to shift to a less crowded service rounds rather than going to the central period. So, and overall, that's in this research that we target to a global optimum solutions, which is the best solution that can reduce the system. And there are also other ways, some research that focus on the suboptimal solutions, which is a second optimal solutions when maybe it's difficult to find a global optimal solutions. But in this scheme and with our design, that we are able to find the best solutions that to reduce the congestions at the maximum levels. And overall, the conclusion that we have for this design and this scheme is that for a given central peak period, if we have already given the central peak period, then we can obtain the optimal reward ratio and a central period location. Well, we also have find out the feasible set of this central period duration, which is from 1 to the maximum of this service rounds departure time schedules. And the global optimum solution can be obtained by the sequential algorithm that we propose in our paper as well. So let's look at a case study so you may have a better idea of how it works. So we use a Copenhagen case study, which this is the metro map. And from this blue dot to this blue dot in the Hellerup station, and it connects with the commuting train. And it's very crowded every morning that people need to come from the suburban area to the central business districts for work. And the current system that in Copenhagen is that from the origin to destination, the base fare is 16.4 krona. And where with our schemes that we propose three different schemes, which we have the refundable surcharge at 3 krona level, 4.1 krona level, and 20 krona level. So 4.1 krona level is the current level. So if they travel in the peak period, with the existing pricing strategies, they need to pay extra 4.1 krona. While we also propose another two to compare the schemes. And then the headway is 3 minutes, and the in-vehicle time takes 12 minutes from A to B, from Holt station to Hellerup station. And there are generally 2,000 commuters traveling in the morning, and the capacity is 700 with 340 seats and 360 standing. And there is a unit cost of scheduled delay early and scheduled delay late, which is associated to their incomes that in that area. And there's also another coefficient, which is economic factors, the coefficient that's based on the economic report of the Denmark National Survey. And here we have a crowding cost function proposed, which the crowding cost function is related to the number of passengers in the vehicle, the number of seats, total seats in the vehicle, and the number of total standing seats in the vehicle. So this comprehensive crowding cost will give us a nonlinear crowding, like shown in this line. So it will increase first with the number of passengers and increases more when the passengers are boarding more. So this actually shows realistic situations that what we used in our case study. And there is also a linear crowding cost, which is as simply linear to the number of passengers here. Here we are using the nonlinear cost. And then the simulation that after the simulation with the optimization, what we find out that this surcharge reward scheme incentive are able to reduce the total trip cost at maximum 7.5%, while crowding cost at maximum 4.8%, and queuing cost is ranging from 34.1% to 9.3%. So it can reduce the queuing cost comprehensively by implementing these incentive strategies. And below, the four graphs shows, the first graph shows what is the current ridership distributions for the different service rounds with the existing surcharge strategies. And then without the surcharge, without the incentive strategies. And then all the rest three shows what will be the predicted ridership distributions after implementing the different design of incentive strategies. And then we can see that there will be a portion of the commuters that are shifting to the shoulder periods. And so this have a kind of dynamic ridership that's for the time of day. While for the overall total system cost, this is how it changes with the contour map. So this is so this dimension shows the central period location. So like it can start at 7, 8, and all the continuous starting time. And then with this dimension, that the total system cost increases first and then decreases at a minimum level and then increases a bit. And then this dimension shows how the system cost will change with the reward ratio. It decreases first and then increases. So let's look at a video to see. Just trying to. So in this video that you will see how the ridership distribution will change based on the reward scheme. So this is when the reward value is increasing, and more people is going to traveling in the shoulder period, while then the ridership in the central period is decreasing, while the ridership in the shoulder period is increasing. And then we also tested for different locations of these central periods. For example, this one covers a large period during the day, while this one shows that there are only few service rounds that are be charged, which the central period time interval is pretty short. So this shows how it changed in the one station, and then there is also simulation that's with multiple stations. With multiple stations, that what it gives is it will give in the multiple stations we count the interrelationship between the different between the upstream stations and downstream stations. So in this case, that the first station have an increased ridership and decrease, while the second station have a little bit less increase of the first station, and then the second station, and so on. And this shows what is the distribution, the temporal and spatial traffic flow distributions in the network level. So all in all, that this incentive strategies, it can be managed that through the flexible design. depending on the existing systems, transit systems. And it also provide alternative operation options that catering for various commuters as it's an individual-based incentives and rewarding. And it's also doable with the current smart card system or with any online platform, with any online resources that can easily track commuters or passengers' departure times and travel choices. And it also showed that it can significantly reduce the trip cost while maintaining the passenger, maintaining the operator's revenue for it. So this is the introduction of the incentive strategies that implemented in that we currently discuss in the transportation systems. And now we're working on more data-driven approaches that to implement this, and also to find the large-scale deployment that are suitable for different cities, different regions, and different areas. Thanks, everyone.
Thank you very much, Dr. Tang, for this interesting presentation. Now we're gonna look for questions. If anyone has any questions, you can raise your hand so I can give you the word, or you can write it in the chat. Yes, David?
Thank you very much. I would like to ask if this can be applied to on-demand transport system like Uber, bicycles, and buses, like Jose Huertas asked.
Yeah. So this actually can be generally implemented to a variety of the transportation systems, because especially for on-demand, because this incentive strategy is a dynamic one, but on-demand also capture the dynamic travel demand that provide the services. So while with the public transit, that this strategy is based on the schedules. This strategy is based on the schedules, which kind of discrete, which have the discrete variables. While with the on-demand services, it will be the continuous changes of the surcharge and reward, as well as the dynamic changes of the real-time changes of the peak hour central period determinations.
Okay, thank you very much.
Thanks.
Thank you. Now, Oscar, do you have a question?
Yes, thank you, Adrian. Yes, please, Professor, I don't know if this can be applied in countries underdeveloping countries, like for example Mexico, where the clothing cost is not so important as the.
Yeah, so is it your question that whether it can be implemented in an area where public transport is not that doesn't have a big market share? Yeah, so while we use this case study for public transit because it shows more straightforward view to people, but the central idea behind is actually focused on to modify the travelers' behaviors in the transportation system. So it can be continuous. It can be implemented in the related transportation systems, as long as it has, congestion issues. It has a peak and valley issues that's in the system.
Okay, thank you.
Thank you.
I have a question about that. For example, here in Mexico, we do use, well, there is people who uses a lot of the public transportation. However, I don't think that crowding is a very good variable. Like, I don't think that they care if it is crowded or not. So to take the bus. So that's a variable that takes a lot of part in this system. How it can be like that change in this kind of situations, or
Yeah, so so for the crowding part, that's let's look at this expressions that the crowding, actually the actual crowding cost for a system will depending on the number of capacity designed in the vehicle, and also depend on the alpha, which is the value of time, value of the cost for the travelers. So it is associated to the society and also economy as well. So let's say in Mexico, that people don't care too much of a crowd. It's maybe because that they have a low cost of this alpha 1, alpha 2, the coefficient, which is related to the social and economic factors. And then, but this do have the effect. It just this effect doesn't maybe doesn't overshadow the other cost. And then in turn that with this different cost, with this different actual formulations, that the design of these incentives are also different, because all the design will be based on the actual cost for the system. And then we turns out our best performance of these incentives, how it can be designed. Does this answer your question?
Yeah, it does. And
Thank
for
you.
example, about the variables of unit cost of scale, delay early and delay late, those are like the minimum wage per hour in Denmark, or you calculated that based on how the people perceive their time?
Yeah, so this is calculated based on how people perceive their time. So there are a variety of the empirical study to investigate what are the actual schedule delay costs for travelers related to their incomes. So it's generally that the value of the actual delay early is around 0.6 to 0.8 of their income, where the scheduled delay late cost is about 1.3 to 1.5 related to their income. And this is based on the empirical study. But of course that's a general values range, but for each specific regions, that if they're specific, if they have already conducted a kind of empirical study to derive this, then we will use that one.
Thank you very much.
Thank
I see another question from Dr. Huertas. However, I think it's the same the Oscar. It says can be used for transport system based on buses. So I think it's the same. Does anyone has any other question? So I think this will be the end of the seminar. Thank you very much, Dr. Tang. We appreciate your time, and thank you very much.